Welcome. This is going to be our lecture video for April 21st. Let's go ahead and get started with a quick review of rational functions. It is going to be pertinent to today's lesson. So at what x value would there be a hole in this graph? So if you can't quite remember our unit of rational functions, you might remember that it's just a good idea to factor everything at the beginning of these problems, and then that would help jog your memory on what the next step would be. So factor first, factoring is always a good idea. Even if you don't end up using the factored form, it doesn't take too long and it's pretty helpful. So with leading coefficient of 1, I can just set up simple factoring here. Then I ask the question, what two numbers multiply to be negative 35 but add to be negative 2? Those numbers are negative 7 and positive 5. And then on the bottom, what two numbers multiply to be 14 but add to be negative 9? Those numbers are negative 7 and negative 2. And at this point, you might see, oh, I've got a matching factor, and then remember, when factors cancel, that causes holes in functions. So this causes a hole, and the hole is specifically at x equals 7. It's not at negative 7, it's at the value that would make this factor equal to 0. We'd have a 0 over 0, doesn't matter what these would be, because of the zero product property, and 0 over 0 is undefined. So our graph would have, we can actually sketch this graph probably pretty decently. Y-intercept is some negative value. I've got an x-intercept of negative 5. I've got a vertical asymptote at 2. So it probably looks a little bit like this. Horizontal asymptote at 1, because this is degrees match, would be 1 over 1. And then right at 7, I'd come up from 7. I'd erase a little piece of my graph, and I draw a circle to represent the hole in this function. All right, and that's just a real rough sketch of what this would look like. But our graph would be totally valid everywhere except for the hole in the vertical asymptote. So now we see we've got some trig functions that also have holes in them. What trig function do we see here? Think real quick, which trig function has a maximum at its initial value and then cycles every 2 pi? Well, that would be our cosine wave. So these are cosine waves, but they've got holes in them. This one has holes at pi over 2, 3 pi over 2, and we can assume if this kept going, it would have another hole at 5 pi over 2, and then 7 pi over 2. This one here's got holes at 0, pi, 2 pi. So how can I write a function that will still be a cosine wave, but will have holes in it? So to figure that out, we gotta go back to this problem where you can add in a factor that cancels on the top and the bottom. And that factor won't affect the shape of the graph except for at that exact value where you get 0 over 0, you'll get a hole. So I'm going to set this up as a rational function. I'm going to put cosine of x on top, and we're graphing in radians here. That should be clear. But now I've got to add a factor to the top and the bottom that will evaluate to 0 at pi over 2, 3 pi over 2, and so on. Well, the trig function that is 0 at pi over 2, 3 pi over 2 is cosine. We can actually see it right here. You can see your cosine wave hit 0 right there, hit 0 right there. So I put another cosine of x on the top and the bottom of this function, and then don't cancel them. This will mean that right when I hit pi over 2, I get 0 over 0, which is undefined, and I get a hole in my function. Everywhere else, these two factors just cancel out, and I get my cosine wave. All right, let's try the same with this one over here. I've got to put a cosine of x on the top, but I need a function now that evaluates to 0 at 0, pi, 2 pi, and that function, you might remember, is sine. So if I put a sine of x at the top and the bottom, they will most of the time cancel each other out, except for right at 0, when sine of x is equal to 0, we'll have 0 over 0. This is undefined, and we'll get holes in our function. Okay, so how do we say that we have a whole every pi over 2, 3 pi over 2, and so on? How do we like show that that list goes on forever? So it's pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, dot, 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 on and on. How do I represent this algebraically? Well, what I do is I'm going to, instead of doing actual numbers, I'm going to do variables. And I need to create an odd number. This is 1 pi over 2, 3 pi over 2, 5, 7, 9. So to create an odd number, you take an integer, you multiply it by 2, and you add 1. This will always be odd, because 2n will always be even, and then you add 1 to any even number, you get an odd number. So I get 2n plus 1, and then we rewrite the rest of this that's not changed into pi over 2. So pi over 2, and then we say comma, n is an integer, n-e-z. N is an integer. N is an element of the integers. That's what that means there. So this is a way to represent that list of all the places where this is going to have a hole. Let's try the same over here. So this one had a hole at 0, pi, 2 pi, 3 pi, we can assume, dot, dot, dot. So this one's actually a little bit easier. This is just n pi, where n is an element of the integers. All right, and this little notation here, you only have to write it once per page, n-e-z, because once you've defined n as being an integer, you're free to just use n as an integer wherever it pops up. All right, so that brings us to our objective for the day. Our goal is to be able to use the reciprocal, tangent, and Pythagorean identities to verify other trig identities. Why we're doing this? By using a simple rule set, we construct complex relationships in trig. So what is this word identity that keeps popping up? An identity is something in math that we assume is true, or I'll say something in math that we don't need to prove. All right, so an identity, something in math that we don't need to prove. So that really brings us to the topic of this next unit, which is going to be really based around this idea of relating our different trigonometric functions in interesting ways. And in order to do that, we need to assume that some relationships are true. We'll prove them once at the very beginning, and then we'll be able to use them to prove much more complex relationships. So an identity, it's similar to an axiom in math. It's something that you don't need to prove. You just sort of take it as true, and then you can go use it to prove other things. And identities normally have to be very simple so that they're sort of like obviously true. So, you know, the most basic identity is 1 equals 1. This is considered to be an identity. Can I prove that 1 equals 1? Well, not really. It's just like by definition a true statement. That is like the definition of equality. So this is an identity. I can't really go any further with this proof. At this point, my proof is done. All right. So here are the identities that we have so far. We know that cosecant of x is equal to 1 over sine of x. Secant is 1 over cosine of x. Cotangent is 1 over tangent of x. All right, and if I take any one of these and rearrange it, like let's take this middle one here, secant equals 1 over cosine, and I multiply both sides by cosine, so now I've got cosine of x times secant of x equals 1. Well, I've just created a new identity because I can assume this is true, so this one must also be true. Now if I divide both sides by secant of x, I'll get that cosine of x equals 1 over secant of x. And there we go. I've got another very useful identity. So likewise, sine is equal to 1 over cosecant, and tangent is 1 over cotangent. Get all these copied down. So, this is just kind of a fact about being reciprocals. If something is a reciprocal of something else, then that relationship holds true in reverse. They are reciprocals of one another. Cosecant equals 1 over sine equals 1 over cosecant. Okay, so there you got 6 trig identities that we can now go out and use. Here is the tangent identity. So when I say specifically tangent identity, I'm not referring to tangent equals 1 over cotangent. I'm referring to this one right here, that tangent of x is equal to, illustrator, sine of x over cosine of x. This is a very useful one because it relates our 3 main trig functions in one relationship. Tangent is equal to sine over cosine. Memorize this one for sure. Most other identities you can just look up when you need, but I would say memorize all the ones on this page. And then definitely memorize this one. Now I will prove that this is true real quick by using SOHCAHTOA. So let me replace each of these with the ratio that they represent in a right triangle. Tangent is opposite over adjacent. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Well, on this side now, I've got a fraction divided by a fraction, so I can copy dot flop that. So opposite over adjacent equals O over H times H over A. Copy dot flop. All right, now I can cancel the H's, and I get O over A equals O over A. And I don't think anyone's gonna argue that this isn't true. That's just our definition of equality. So that proves that this is true. Tangent equals sine over cosine. Use this one almost every time you see a tangent. You want to replace it with sine over cosine. All right, let's talk about this idea of domain of validity. So this is why we did these fancy pictures here, is because these lists, these help us establish our domains of validity. So what is the domain of validity of cosine equals 1 over secant of x? So a couple ways to think about this. But what I want to do is I want to replace cosine and secant with the ratios they represent. I want to say cosine is adjacent over hypotenuse, and secant is hypotenuse over adjacent. We can see why this relationship is true now, because if we just copy dot flop to the right hand side, we get A over H equals A over H. But I want to look now for any side length that's in the denominator. We've got adjacent in the denominator. Hypotenuse counts as being in the denominator because it's on the bottom of this bigger fraction, and this one as well. So the hypotenuse in our unit circle is never going to be 0, but adjacent can sometimes be 0. So when is the adjacent equal to 0? Because if the adjacent is equal to 0, this relationship will stop being true, because I'll have 1 divided by 0 over here. It'll be undefined. So I'll have 0 equals undefined. That's not a true statement. So for this identity to be true, we need to exclude some x values that cause secant of x to be equal to 0. So when is the adjacent equal to 0? Well, that's when x is equal to pi over 2, 3 pi over 2, 5 pi over 2. This should look familiar. This is our 2n plus 1 pi over 2, where n is an element. We do a fancy little e here of the integers. All right, and that's because this corresponds with when cosine crosses 0. So cosine starts at a maximum. After 2 pi, it comes back to a maximum. But at pi over 2 and 3 pi over 2, it hits 0. And that's because the adjacent becomes equal to 0. So what we need to say is that x cannot equal this list here. And as long as x does not equal any number in this list here, then this identity is true. But when it does, then you've got 0 equals undefined. That's not true. Everywhere else, this relationship holds true. All right. What about this one? Sine of x equals 1 over cosecant of x. So this is opposite over hypotenuse equals 1 over hypotenuse over opposite. So the side lengths that ended up in the denominator are hypotenuse, which we said can never be equal to 0, and opposite. So when is opposite equal to 0? Well, that happens at 0, pi, 2 pi. This is that list of n pi, where n is an element of the integers, and then we have to say x cannot equal that. Okay, and last one, domain of validity of tangent equals 1 over cotangent. So tangent is opposite over adjacent. Cotangent is adjacent over opposite. So the side lengths ending up in the denominator here are adjacent and opposite, are all in the denominator. So when are either opposite or adjacent equal to 0. So we've got to kind of combine our two lists. So opposite was equal to 0 at 0, pi, 2 pi, and so on. Adjacent was equal to 0 at pi over 2, 3 pi over 2, 5 pi over 2, and so on. So how do I represent all of these? Well, I need to put it into, a form where things are just only one part of it is changing each time. So I'm going to represent this as a 0 pi over 2, a 1 pi over 2, a 2 pi over 2. Notice the 2's would cancel, I'd get a pi back. 3 pi over 2, 4 pi over 2. Hopefully we see the pattern here. We can represent this as n pi over 2, where n is an element of the integers, and then we'll say x cannot equal that. Okay, so I know this seemed like a lot, but those are the only 3 domains of validity possible. Well, I guess the fourth is technically x can equal all real numbers. There's no restrictions. That one's more rare. You normally get at least one of these side lengths in the denominator somewhere. But you could just write this down and then reference it every time you need it, is that if adjacent ends up in the denominator, the domain of validity is this. If opposite ends up in the denominator, the domain of validity is this. And if both of them end up in the denominator, the domain of validity is this. All right. Here's one from the homework. We're going to attempt to verify this identity. So we want to show through using just the tangent identities and the tangent identity and the reciprocal identities that this is true. So every time you use a reciprocal identity, draw an arrow with an R. And every time you use the tangent identity, draw an arrow with a T. So this is for a reciprocal. And this is for the tangent. And that's all you're going to need. Well, actually, I think there's some on there that use the Pythagorean identity. But this homework, it was supposed to be due in a week. So you're going to have time to learn that before this homework is supposedly supposed to be due. So if you see any trig functions squared, you can skip those until you know about the Pythagorean identity. All right, but this one only uses reciprocal and tangent. So sine, I'm not going to change. Secant, I am going to change. I'm going to make that 1 over cosine. Also, one thing is I drop all of the x's when I'm doing this. So I'm just going to have this equals sine times 1 over cosine. Right there, I used a reciprocal identity, so I put an R on that arrow. And cotangent, I think it's worth learning this one right now. So if tangent equals sine over cosine, then cotangent equals cosine over sine, because cotangent is the reciprocal of tangent. So to find its tangent identity, you just flip this side upside down. So there I just used a tangent identity. I'll put a little t there, and I'm going to write this as cosine over sine equals 1. All right, the sine's going to go up top. I've got now sine over cosine times cosine over sine. We're going to cross cancel the cosines and the sines, and then we get 1 equals 1. And when your verification is done, once you've reached something like 1 equals 1, or just anything where we can use just the definition of equality to say that this is true, you draw a little box. Okay, I'm going to be doing a whole bunch more of these on the homework help video, so definitely watch that. Trying to explain more about what's going on here, but we just verified that this identity here is true. All right, have a great day.